Section 3.5, Exponential and Logarithmic Functions. The objectives of this section are to identify the form of an exponential function and its properties, identify the form of a logarithmic function and its properties, understand and apply the relationship between exponential and logarithmic functions, and finally to solve exponential and logarithmic equations. So begin with the definition of exponential functions. An exponential function is a function of the form y equals to a times b to the power of x, where x is any real number, and a and b are basically numbers, but b cannot be equal to 1, and it must be greater than 0. The number b is called the base of the exponential. So the important thing to remember here is that the x is in the power. So this is different than the polynomials where x is in the base and the power is a fixed value. Here we have a base that is a fixed value and the power continuously changes. So that's where the x is usually. So this is an example of what we call an exponential function, but there's also things like 5 times 3 to the power of x, which we would call also an exponential function. So as long as x in the power has power 1, then we will call it an exponential function, and in this class that's the ones we're interested in. So we begin by plotting some of these exponential functions, and we're told in example number 1 to plot the graph of y equal to 2 to the power of x and y equals to 1/2 to the power of x by completing the table. So I'm going to be using the table method here, but you can use your calculator to graph these two exponential functions, and they are exponentials because the base here is fixed, it's equal to 2, and the other one is also an exponential function because the base is fixed and it's 1/2. And notice how the power contains the variable x. So this is the reason why we call these exponential functions. So the calculators can help us with graphing, but for now, let's begin by doing the process by hand. So we're provided a small table and we're told to graph to the power of x, and we are supposed to plug in the values -3, -2, -1, 0, 1, 2, and 3. And so this is a pretty straightforward application. You just plug in the power is supposed to be -3, so 2 to the power of -3 is going to be the same thing as 1 over 2 cubed, which is basically 1 over 8. Similarly, 2 to the power of -2 is basically 1 over 4, and so on and so forth. So 2 to the power of -1 is going to be 1/2, and we get to 2 to the power of 0, and anytime the base is not 0, but we have a power of 0, this is always going to be a 1, so 2 to the power of 0 is equal to 1. Next, we have 2 to the power of 1, which is going to be just simply 2. And next is 2 squared, which is really 4. And finally, 2 cubed, which is really 8, because 2 times 2 times 2 is equal to 8. Now, you can get these values again with your calculator, but in this case, I can just find them by hand very quickly. Let me do the second half of the table. So in this problem, we're supposed to plug in -3 as a power of 1/2, so 1/2 to the power of -3. So the way I think about 1/2 to the power of -3 is I think about it like this. 1/2 needs to have a positive exponent. So how can I make it have a positive exponent? Well, what I need to do is put it on the denominator. So it's going to be basically 1 divided by 1/2 to the power of 3. That's one way to think about it, but this is the complicated way. Another way to think about it is to just give the exponent -3 to the numerator, so you get 1 to the power of -3, and give the exponent -3 to the denominator. So basically 2 to the power of -3 again. And anytime you have a negative exponent, it just means that the base wants to be on the other side of the fraction. So this 1 does not want to be on top, it wants to be on the bottom. So I put it on the bottom and I make the power positive. In the same way, the 2 to the -3 doesn't want to be on the denominator. I need to put it on the numerator. And when I do that, I just lose the minus from the exponent. And so now it's basically 2 cubed, which is 8, divided by 1 cubed, which is 1. And 8 over 1 is really just simply 8. So in the same way, we can pretty much finish the rest of this table by doing the same process. So next, I'm supposed to do 1/2 to the power of -2. Well, that's going to be just simply 4. Next, I'm going to have 1/2 to the power of -1, and that's going to be simply 2. Next, 1/2 is the base, and we're raising it to the power of 0. And like we said earlier, anytime the base is not 0, but it's raised to the power of 0, the answer is always going to be 1. And finally, 1/2 to the power of 1, well, that's just 1/2, and 1/2 squared is going to be basically the way I think about this is I say, okay, the 1 has to be squared, and the 2 has to be squared as well. And 1 squared is really 1, 2 squared is really 4, so we get 1/4. And finally, 1/2 must be cubed, and this is going to be just simply 1/8. And again, that's because 1/2 to the power of 3 is really 1 cubed divided by 2 cubed, and 1 raised to any power is 1, but 2 cubed is really 8. So now that I have the table completed, I'm just going to transfer the points to my graph and plot the points. So first point on the table is x equal to -3, but y is equal to 1/8. This is going to be very, very small. It's about 0.1, so this is the first point on my graph. The second point on the red graph is going to be where x is -2, the y is 1/4, so this is 0.25. Again, it's very, very small. So it's going to be somewhere around there. The next point is -1 with 1/2. So when x is -1, the y is 1/2. So we're at 0.5 now. And you can see the points are very low at this point in time. Next, we have 0 with 1. So when x is 0, the y is 1. So we're basically crossing the y-axis at 0, 1. Next, we have 1, 2. So when x is 1, the y is 2. And we continue the same way. When x is 2, the y is going to be 4, so 2 gives us 4. And finally, the last point we have to plot is 3 gives us 8. So when x is 3, the y is equal to 8. And as you can see, the points start going up very quickly. So the graph should be a nice, smooth kind of a curve that passes through all the points that we just drew. And so this is the way it's going to look. So this is the graph of the function that we're calling y equals to 2 to the power of x. And so similarly, we're going to graph all the blue points. So remember, the x value is here and the y value is there. So when x is -3, the y is going to be 8. So we start very high. We're starting on the other side there. So that's -3, 8. And then we have -2 with 4. So -2, 4 gives us a point there. Next, we have -1 with 2, so the point is going to be here. Next, we have the point 0, 1, so we're crossing in the same spot on the y-axis. When x is 0, the y is 1. And we continue with x equal to 1, we get 1/2. With x equal to 2, we get 1/4, so 0.25. And finally, with x3, we get 1/8, which is roughly speaking about 0.125. So again, the curve that we are going to draw is going to connect all those dots and make it as nice and smooth as possible. The important thing here is that you should not make it cross the x-axis. As a matter of fact, so these exponential functions, in this case it's 1/2 to the power of x, they both have what's known as a horizontal asymptote. So the horizontal asymptotes are basically lines that we don't draw. They're basically imaginary, or not imaginary, but they're lines on this graph that the graph cannot cross. Think of it like a border. And in this case, it's the same for both of the graphs. So in this case, the line that we're not able to cross is the x-axis itself, right? So the graphs approach this line, but they never cross it. So we would say that the x-axis, which has equation y equal to 0, is a horizontal asymptote. I'm going to write HA for horizontal asymptote. So remember, these are lines defined by what happens as x goes to infinity or as x goes to -infinity. So as x goes to infinity, ask yourself, what's happening to my graph? Or as x goes to -infinity, what's happening to my graph? And in both cases, as we can see from the graph, for the blue one, as x goes to +infinity, the graph tends to become kind of horizontal. It's going to be very, very close to the y equal to 0, which is the horizontal asymptote, meaning the x-axis. And similarly, this red one, as x goes towards -infinity, the graph tends to get closer and closer to 0. It's never ever going to touch 0. That's why we say y equal to 0 is a horizontal asymptote. Okay, so if you are not able to kind of see the horizontal asymptote, just think about what would happen if you plugged in more values in this table. Will you ever see a value of 0? The answer is no. No matter what we plug in for the power, the return is never going to be a 0 value. So to summarize what we just did, we graphed the functions y equal 2 to the power of x, and we graphed the function y equal to 1/2 to the power of x. And in both cases, we saw a graph that is continuous, meaning we were able to graph the whole thing without lifting our hand. the graph was also positive in both cases, meaning it was always above the x-axis. In both cases, we saw that it crosses the y-axis where x is equal to 0 and the y is equal to the base. So that's what we're graphing here as well on this page. And we notice that if the base is more than 1, so in this case it was 2, for example, we notice that the graph starts very low and it goes very, very high very quickly. And on the other hand, if the base is a number between 0 and 1, so in this case we had 1/2, we notice that the graph starts very high and it goes down low very, very quickly. So this summary on this page is supposed to help you remember how you can graph the function without having to make a table every single time. So if you remember, all that really matters is the base. If the base is more than 1, then the graph will generally look like it's going up from left to right. And if the base is between 0 and 1, then the graph should be going down as we go from left to right on the image. And also there's some important points that we always will cross through. So for example, we always cross through the point 0a. So this is 0 comma the base of your problem. And there's another point where if you plug in 1, you're going to get the base raised to the power of 1, which is just the base. And if there's a constant multiplied by the base, then that's the y coordinate that needs to go there, or in this case here. So with this in mind, let's take a look at how we can graph the functions using the calculator. So let me go to my calculator, and we are going to go to the y menu and first plug in 2 to the power of x. So this is how it looks for the newer TI calculators that have the math print. But if you don't have the math print, then this is where it's going to look like for you. So let's go ahead and switch it from math print to classic. So this is the way the old school calculators would show it. It's just the 2 with the caret and then x. And let me put the other one also. So 1 over 2. And notice how I'm putting parentheses around my whole base, because if I don't, the calculator might misunderstand what I'm trying to graph. So I want to graph 1/2 to the power of x. So again, I can put the x without parentheses, but the base needs to be inside parentheses. And let's click on zoom, then 6, and that will set it in the standard window from -10 to 10 on both the x and the y coordinates. And as you can see, the graph is doing exactly what we expected. By the way, you can click on trace and trace some of these values. So for example, notice how 0, 1 is on both graphs. It's on the blue graph and also on the red graph. This is what we expected. When you plug in 0 into the base, into the x, sorry, you're going to have the base to the power of 0, which is always going to be 1. This is the reason why we're always going to cross through the point 0, 1. And also, when I try to trace, for example, 1, then you'll see I always pass through 1, 2 in this case, because 1 is x, or x is a 1, and 2 to the power of 1 is really 2. So I just get the base basically back. If I'm on the red curve and I plug in 1, then also notice how we get 0.5, because 1 over 2 is 0.5. So this is how you can graph the function and verify that the graph is correct. Let's look at the table. So our table here has some built-in values, and the way to enter the table is I click second, and then I click the graph button. That gets me into a table with some random numbers in here. But if you actually want to plug the numbers yourself and see what y values you will get, then let's do that next. So let's click on second, then window. That gets us into the table setup. And from here, I'm going to go down a couple times and reach the independent line. Currently, it says auto. I'm going to switch it to ask. So this will force the calculator to ask me for the x values that I care about. And in return, it's automatically going to give me the y coordinates for free. So once you have switched it to ask, just click enter to save your settings. And you can now click second graph, and you'll see your table is now empty. So I can plug in -3, for instance, and it will say 0.125, which is the 1 over 8, and also 8, which is the second coordinate that we have. -2 gives us 0.25, which is 1/4, and the second coordinate is 4 on the other graph. And similarly, we can plug all the values that we care about, and we can see that we are correct in our answers on the paper. We had the same values, except our numbers were not decimals, they were fractions, and the calculator gives us decimals. So you can produce the table that you want here and then transfer it to paper, or you can just click graph and see the graph on your screen and then translate it back to your page. So this is why I'm not focusing too heavily on how to graph these exponential functions, because you could always do what I just did, get the graph here, and then transfer it to paper very, very easily. But I want to point out that the graphs become sort of horizontal as you go, for example, on the 2 to the power of x. As I move closer or farther and further to the left, notice how the y-coordinates on the bottom of the screen are basically becoming very, very close to 0. They're never reaching 0. So in this case, I'm seeing 0.0014, but they never reach 0. And that's why we say y equal to 0 is a horizontal asymptote. So it's like the border, right? We're trying to get to 0, but we're not able to. And in the same way on the red graph, if I go, for example, to the very right side of the graph, you'll notice that the numbers get smaller and smaller. Again, they can never reach 0, but they are trying to get to 0. So if you keep going more and more to the left, you'll see that the numbers become very, very, very small, but they never ever touch 0. And that's why we say that y equal to 0 is the horizontal asymptote. Okay, so let's continue our discussion with natural exponential function next. And what we mean by the natural exponential function is that it's a function with the base e. So there's a new number that we're going to talk about next right now, actually, and that's e. And e is a special constant. Just think of it like a pi, right? Pi is, roughly speaking, 3.14. Think of e as a constant similar to pi. It's actually got a value of 2.718, and it goes on forever, actually, just like pi goes on forever. They are both irrational numbers, meaning the decimal does not end, it does not terminate, and it doesn't repeat. So the pattern is completely random. We don't know what number is going to appear here next until we actually do the calculation and find out. Now, how is this number e defined? It's defined as a limit, and the limit is limit as n goes to infinity with 1 plus 1 over n all to the power of n. So this limit is supposed to evaluate the number e for us. And I'm showing you here in this table on the middle of the page that when you plug in, for example, 10 for the n, so if I replace the denominator with 10 and the power with 10, then the value I will see on my calculator screen is going to be 2.5937. But if I switch the 10 to 100, for instance, then my value becomes 2.7048. And we keep doing that. If you eventually plug infinity and infinity there, which we can't really because infinity does not exist, it's an idea. Basically, it's saying plug in really massive numbers. But as you do that, if you plug really big numbers, then you'll start to notice that the number converges to this value, 2.7182. So for our intents and purposes, you could just remember that it's 2.71. And if you want to find it on your calculator, if you ever forget, then here's how you can do that. So on your calculator, there's a special button for E. Right next to the key for 4, there's a button that says ln on it. But we don't want ln yet. We want the E, which is for me in blue. Maybe on your calculator it's in yellow. So to access it, you're going to click second, then click the key right next to 4, which is the ln key. This puts E, and then you can give it whatever power you want. So for now, I'm just going to give it power 1, and you'll see that it's 2.7182 like we predicted. So that's how you're going to find it on your calculator, and we need it because we were going to do a lot of calculations with it as well. So it's helpful to know how to do it. So if I wanted to know what's E times E, or E squared, I would go second and then click the key next to 4, and then I would type in 2, close parentheses. This means I want to multiply 2.71828 and so on by itself twice. And so the value will be 7.38 and so on and so forth. You can also plug in negative values. For instance, you can plug in e to the power of negative 0.025, and the value will be on the screen. So it accepts any positive exponents or negative exponent regardless. So that's what the value e is. And where does it appear? It appears in business calculations or business applications, and we'll talk about one of them in a few minutes. So before I get there, let's talk about this formula on the middle of the page, which is the formula that is used to compute the value of an investment when an account earns compound interest. So basically, you drop your money in the bank, and the bank gives you, let's say, 10% every month, and you leave your money in the bank for a couple of years. Well, how much money will you expect at the end, right, when you come back and pick it up? That's what we call A. That's the future amount that you're going to have after you've given your money to the bank or you've invested it in some kind of a scheme that gives you interest regularly. P is the principal. It's the amount that you are investing. That's the amount that you are given to the bank, and you're telling them, hey, keep this, use it, whatever, and give me interest. R in this formula is the rate of interest. So usually that's a percentage. So it could be 10%, it could be 1%, it could be 0.5%, who knows. N in this formula shows up twice, and it's the number of times that you're given compound interest per year. So if you're given it at the end of each month, then N would be equal to 12 because you're given 12 payments per year. But if you're given interest maybe every day, then the N will be 365, for instance, because that's how many times you're given interest per year. And T is that last variable there in the exponent, is the amount of years you're investing your money with this bank or with this scheme, basically. Now, as you can see, there is no E in this formula yet, but we will get there in a couple of minutes. After we go through some of these calculations, we will see how this formula creates, or how this formula turns into something that requires E, the number 2.7. So with this formula in mind, let's go look at example number 2, which says, suppose $10,000 is invested in an account earning 8.5% interest. They want us to determine the value of the investment after 10 years given various compounding scenarios. So there's going to be multiple parts in this problem, and they all rely on this assumption that you're investing $10,000 in an account earning 8.5% interest. And how long are we investing it for? We're investing it for 10 years. So let's begin by giving some of these a variable. So this 10,000 is the amount I'm investing. That's going to be my P, the principal. So that's P. So it's going to be the same for every part of this problem that we do. The amount is earning 8.5 interest. So something is 8.5%. And this is basically what we call R in these problems. So R, the amount of interest, is going to be 8.5%. And actually, I'm going to convert it to a decimal. So let me make this a little bit bigger. And as a decimal, it's 8.5 divided by 100. You can put this in your calculator if you don't know, but it's 0.085. That's what I meant to say. And so that's the interest rate. And finally, 10, something is equal to 10. 10 is actually going to be the time. This is in years. And so 10 is the total time we're investing our money with this bank. So they want to know how much money I'm going to have, or you are maybe interested in finding how much money you're going to have if the interest is paid out once a year. So to know, we just write the formula. A is equal to P times 1 plus R over N to the power of NT. And for us, this means the following. First, A is what we're looking for. P is the principal. That's going to be for us 10,000. So 10,000 goes first here. And we are going to multiply it with 1 plus R, the rate of interest, which is 0.085. all divided by n. So in this problem, we are told that the compounding is happening annually. So what does that mean? That means that n is equal to 1 because you're only getting one payment every year. So n is going to be 1, and it's raised to the power of 1 times the t, which in our case is 10. So let's color code everything. So this is the t, and this is the r, the rate of interest. And n is 1 in this problem, and P, the principal, is 10,000. So at this point in time, I just have to take this and plug it into my calculator and see what value the calculator will give me, and that will be the end. So let's find out what is my amount gonna be in 1 year. Sorry, in 10 years. So going back to the calculator screen, I'm going to basically type in 10,000. So let's make sure we add 4 zeros times 1 plus the rate of interest. The rate of interest is 0.085. It's divided by 1. I really don't need to put the 1 here, but I'm going to put it just for completeness sake. Now close the parentheses, and we will need to raise it to the power of 1 times 10. Now again, I know what 1 times 10 is, but just to make it kind of clear, here's how we type it in with all the parentheses and everything else. Once I click enter, I'm going to see that the amount is roughly $22,609. So let's just transfer that to our page, and we will write in 22,609 point, let's say 83. So this is an amount in dollars. And so if I give my $10,000 to the bank and I'm earning 8.5 interest per year, and I'm earning it once a year, then I can expect to find $22,600 roughly in 10 years. So now we're going to do the same thing again, but this time we're going to figure out what the amount will be if I'm getting interest semi-annually. So semi-annually means what? Semi-annually means that you're getting 2 payments per year. So n will be equal to 2 instead of 1. But everything else is the same. So a is going to be 1 plus, sorry, it's going to be p times 1 plus r over n to the power of nt. And keep in mind that the p is 10,000, the rate of interest is 0.085, and the only thing that's changing is the n becomes a 2, and the power will be 2 times 10 as well. So roughly speaking, how much is this? So again, we go to our calculator, and all we really have to do is just change the 1 on screen to a 2. So the way I'm going to do that is I'm going to click second, enter. That brings back the previous line that I just typed in, and that's kind of why I had put in the 1s earlier. So now I could just very quickly go back with my arrows and replace the 1 with 2. And same thing again here with the power. I can replace the 1 with 2, and the value that I'm seeing on the screen is 22,989.063. So let's just say 06 because we're rounding to 2 decimal places. This is money, can't go any further anyway. So transferring this to our page, we are going to write here 22,989.06, and this is a dollar amount. So obviously, if I'm getting interest twice a year, it's a little bit better for me. I went up by a few $100s. And next, we are compounding monthly. So monthly means that n is 12 because there are 12 months in a year. So same thing again, it's the same exact calculation, except the only thing that's going to change is the n in the denominator and the n in the power. Those are the only things that will become 12. So I'm going to just copy paste all this and just change just a couple of numbers. So I'm going to put 12 and 12, and let's see what the answer is going to be. So like I said, we're only changing the n to 12, and so in my calculator screen, I'll need to go back and bring back the previous values that are plugged in, and I'm going to go back and just click second and then the delete key. This will allow me to insert the 1. So instead of 2, now it says 12 on the denominator, and I want to do the same thing on the numerator. So I'm going to click second and then the delete key. That will allow me to insert the 1 and turn the 2 into a 12. And we see the value 23,326.471, so we'll just round to 47. So let's transfer that here. So we said 23,326.47. Okay, so for the next part, we are told that we are getting interest compounded weekly. So weekly means that n is going to be 52 because there are 52 weeks in the year. So again, the process is going to be the same. I'm going to copy this whole formula, and actually the only thing that's going to change is, again, as before, the power is going to be 52 times 10 instead of 12 times 10, and the denominator is going to be 52 rather than 12. Everything else basically stays the same amount where it's being invested every single time, and it's the same number of years, 10 years, so same principle. So again, the only thing I need to change on my calculator screen is the 12. I need to make it 52. So I'm going to click second enter, go back all the way to the denominator and type 5 on top of the 1, so that makes it 52. And same thing again in the x one. So 52 times 10 will be 23,380. So you see we are getting about, $50 more if we're compounding this often. And the decimal is 23/8, so we'll just say 24. We're rounding to 2 decimal places. So the answer here will be 23,380.24. You know what? Let me just erase some of these things so that we're not getting all the numbers confused with each other, so we can see which part is which. But the formula is basically the same every single time, and I think by now you kind of recognize that. So let's keep going with the next part, which is daily. So we're getting compound interest daily. So daily means that n is going to be 365. So at the end of each day, we get interest. So again, I'm going to just grab this problem and copy paste it, but the only thing I'm going to change is the n. I'm going to switch it to 365, and it used to be multiplied by 10 on the exponent, and it's 365 on the denominator. So that's the only change I gotta make on my calculator, is the 52 needs to be changed to 365. So going back here, this is getting a little bit crowded, so let me clear it and then just bring back the last entry. So I would like to have 365 instead of the 52. So let's do this. I'm gonna go back and click second delete and insert 365 on the denominator. Then I'm going to just delete 52. And same thing again on the numerator. I'm going to click second, insert, and then put 365. Then I'll just click the delete key to delete 5 and then delete the 2. So this will be roughly $23,394.15. Okay, transferring it to page 23,394.15. Okay, so far these are the regular common calculations that you have to do in this class. So, try to remember what these words actually mean. That's the only thing that really you need to pay attention to here. We're doing the calculation over and over again, and you're kind of learning how to plug it into the calculator, but that's a minor skill to develop. And finally, we get to the complicated one, which is hourly, right? So hourly, that means we have to do a little bit more math here, because I don't know off the top of my head how many hours there are in a year, but I know that there are 365 days in a year, and each one of them consists of 24 hours. So we can type in this thing into the calculator and see how much n is going to be, basically. So 365 times 24 will give us 8,760. So that's the number for n, 8,760. And again, it's the same thing as before. I'm going to copy paste all this because nothing really much is changing. It's just n, instead of 365, it's going to be this new value, which is 8,760, and it's going to go in the exponent and also in the denominator. So that's the only thing that's really changing, and let's plug it into the calculator and see what happens. So in this problem, I just typed 365 times 24 on the screen. So the last entry, if I type in second enter, is going to be that. So just do it again one more time. Just click second enter another time, and it will recall the previous entry to that. So I had to do it twice to get to the one that I see on top of my screen. And what I want to do is go back a few steps and insert the value that I care about, which is 8,760 in the denominator. Then erase 3, 6, and 5. And same thing again in the exponent. I'm going to go back and insert the 8,760. And I'm going to delete the 3, the 6, and the 5. So it looks right. And here we go. 23,396.37 with 1. So we're just going to round to 37. Okay, so the answer was 23,396.37. Okay, so far I think it's been pretty standard. The last step was maybe the most difficult one because we had to figure out how many hours there are in a year. But now the interesting thing is what's happening here with continuous interest. So with continuous interest, that means I'm getting interest every second of every day. That means that n is really, really big. right? So every second of every hour, you're getting interest. Every split second, you're getting interest. So n is really infinity. So my value should be 1,000, or rather 10,000 times 1 plus 0.085, all divided by infinity to the power of infinity times 10. And unfortunately, this does not work. We cannot plug this into the calculator. There's no key even for infinity. And really, infinity is just an idea that says really, really, really big numbers. So this is not going to work for us, but thankfully there's a second formula for the continuous version of this problem. The formula is the one that you see down below. So if your amount is being compounded continuously, then instead of using the original formula with a equals to p times 1 plus r over n to the power of nt, you will have to use this new formula, which is a equals to p times e to the rt. And this is where that letter e that we talked about earlier, the new constant, the 2.7 something, is going to appear. So in my problem, that means I'm going to multiply 10,000, because that's my principal, by e, which there's a key for that on the calculator, and the r is 0.085, that's the interest rate, times, in this problem, 10, because that's how many years I am investing my money for. So A is going to be, roughly speaking, let's see, we will plug it into the calculator to see what this gives us. So on my calculator screen, I'm going to clear everything so you can follow along. First, I'm going to type 10,000. Then I'm going to multiply by the E. And remember, E is that new key right next to 4. So I'm going to click second and then the ln key to bring E to my screen. So now I need to type in the exponent, and notice how the calculator automatically puts a caret and a parentheses because it's expecting an exponent to show up next. So I'm going to type in 0.085 and multiply that by 10 years. Close the parentheses and then just hit enter. And there you have it, 23,396.468. So I'm going to round up. So instead of 46, I'll say 47. So the answer here was 396.47 dollars. So this is the best case scenario. You're going to get the most money. Right? It's about 10 cents more than if you were getting the interest compounded hourly. So it's best for you as the investor to have your money compounded continuously. That means you're constantly getting interest and you can pull your money out at any moment in time, and you're guaranteed to have the most money possible. So that's how E shows up in these types of applications. But regardless, we are going to see it in different types of settings. So this is just one of them. So in example 3, we're basically repeating pretty much what we did on the previous page. We have two scenarios, and we're going to compound one of them quarterly and the other one continuously. So this is just a summary of what just happened so far. It says, compute the future value of the investment given each situation. So the future value means that we want to compute the A amount. And we're investing for the first time $5,000 at the interest rate of 7.25. It's being invested for 9 years, and it's being compounded quarterly. So let's record what each one of these things mean. So P is 5,000. That's because I am investing $5,000. That's what that number means. The 7.5% is the rate of interest. So R is 7.25%, which we can write as 7.25 divided by 100. And all I have to do really is move the decimal a couple times to get 0.0725. It's better to have it this way because later on we'll need to plug it into the calculator. So this really is just the rate of interest. And lastly here we have 9 years. Well, that means that t is equal to 9. And finally, the last thing we need to record is that the amount is being compounded quarterly. So that means n is equal to how much? Well, there are 4 quarters in a year, so that means n is going to be equal to 4. So n is equal to 4, and now we are ready to find the value of a. So given all this, we can say that a is equal to p times 1 plus r over n to the power of n times t. So this formula you need to memorize. Nobody is going to give it to you on an exam or a quiz, so you need to know it. So for us, that would be something like 5,000 times 1 plus r, the rate of interest, which is 0.0725, all divided by n, which is 4, to the power of 4 times the t. The time is 9. So calculator time, we'll plug it in and see what the value is. Let me clear what's on screen, and we're going to type in 5,000 times 1 plus the rate of interest, 0.0725, divided by the n, for us it's 4, to the power of nt. So remember, there are two numbers that need to be in the power, so make sure you use parentheses. If you don't, the calculator will raise everything to the power of 4, then multiply the whole answer by 9, which is incorrect. We want to raise it to the power of 4 times 9, meaning 36. And we are getting 9,545.74. Again, it's money, so I'm going to round to 2 decimal places. So I'm just going to say 74 instead of 741. So the amount that I'm going to be getting is $9,545.74. And for the next part, we are investing $1,500 with a rate of interest of 4.5% for 20 years compounded continuously. So that word is the key to tell me that the formula I need to use is A equal to P times e to the r times t. So I'm writing r in cursive and t in cursive. So P in this problem is going to be 1,500 because that's the amount I'm investing right there. And r, the amount of interest, the rate of interest is 4.5%. And again, it's better to have it as a decimal, so we can write it as 4.5%, meaning divide by 100. Then just move the decimal a couple times, you get 0.045 as your interest rate. So I'll color that in blue like I always do. So that's where the value is going to be. It's going to be in the exponent. The p is in front as a big number. And finally, t is 20 years. So time in this problem, we're investing the money for 20 years. So that's going to go in the exponent. And the word continuously means I should be using this whole formula. Okay. So for me, all this means that A is equal to 1,500 times e to the power of 0.045, all multiplied by 20. So let's see. Again, calculator is going to help us find out what these values are. There's no way I could really do this by hand. So let's switch up to the calculator and type in the 1,500 multiplied by the e, which again, I click second and the key next to 4 is ln. That gives me the e. Later on, in the last parts of the section, we'll use the ln key, but for now, we want the e, which is in blue or yellow, so you always have to click second first. So 0.045 times 20 years. And the answer is 3689.404. So we're just going to round it down to 2 decimal places. So it's going to be 3689.40. And that's what we're going to record over here on our page, 3689.40. So $3,000 and $689.40. That's the final answer. Okay, so now let's look at another problem where we have an exponential function. In example 4, we're told that the demand D in millions of barrels for oil in an oil-rich country is given by the function capital D of little p equal to 150 times the base 2.7 to the power of negative 0.25 p, where p is the price in dollars of a barrel of oil. So as you can see, this whole formula here is an exponential function because the variable is in the power. The base in this case is 2.7, and 150 is just a constant being multiplied by the base that has the variable exponent. P is supposed to be the price in dollars for a barrel of oil, and capital D is the demand in millions of barrels. So what are we willing to, or what are we asked to find? We're asked to find the difference in the amount of oil demanded to the nearest million barrels when the prices increase from $15 to $20 a barrel. So this is a straightforward application of just plugging in the numbers into the formula and then just calculating the difference. So what we're asked to find basically is we are supposed to calculate D of 15, so figure out how much the demand is when the price is $15, then figure out what the price or what the demand is when the price is $20, and then just find the difference of these two. So next we'll just do D15 minus D of 20, and that will be the answer that they are looking for. So for 15, I'm just going to type in 150 times 2.7 to the power of negative 0.25 and replace the p with 15. So that's straightforward. Because I'm given 15, I just replace p in the exponent with 15, and we'll put this in the calculator in a second and see what the value is going to be. In the same way, I'm going to do the second one. Type in 150 times 2.7 to the power of negative 0.25, but the p has been changed to 20, and again, I need to figure out what the value is going to be, and we can use our calculator to do this. So speaking of which, let's switch over to the calculator. So for the first one, we have 150 times 2.7 with power, so I need to put that little caret. And I have multiple numbers and multiple things going on in my exponent, so make sure you use parentheses. So start with negative 0.25, and we're multiplying that by 15 for the first value. And the value is going to be roughly 3.61807. I'm just going to say 3.618 because of what they asked us to round to. So the second one is going to have the 15 changed to 20, so I'll click second enter to bring back the previous entry that I typed in. And go back, instead of 15, I'll just type in 20. So directly on top of it, I could just write 20. It's the same number of decimals, same number of digits, so 1.045. So if you increase the price from $15 to $20, obviously the demand is going to drop because less people are going to want to buy the oil. It's way too expensive now. So 1.045, and I'm routing to the nearest million barrel, so 1.045. So let's record those here. So we said the first one was 3.618 millions of barrels. So millions of barrels. And the second one was 1.045 millions of barrels as well. So I'm just going to copy paste this to here. Okay, so finally, they want to know what's the difference in demand when you increase the price. So how much are we losing in demand when we increase the price from $15 to $20? Well, it's going to be the first answer that we got minus the second answer that we got. And we can, again, plug this into the calculator to see what the value is. So here we go. So I'm going to go to the first answer and just click enter. So I did that by going up to the answer that I want and then selecting it by hitting enter. So I want to subtract the second answer that I got and hit enter one more time. So roughly 2.5726. So because of the 6, I'm going to say 2.573. So 2.573. And again, this is in units of millions of barrels. So I'm just going to copy paste that to the answer. So this is a straightforward just application of how to plug things into the calculator. And to just remind you that just because we did a few problems with bases with 1 plus r over n doesn't mean that's always the same. The base could be anything. In this case, the base was 2.7. And sometimes the base is e, which is roughly 2.718, and so on and so forth. Okay, so now let's talk about logarithmic functions. The bottom line is logarithmic and exponential functions are inverse functions, meaning one of them will undo the other one. Basically, that means that they are functions whose input and output have been interchanged. So if I'm starting with a function called f of x equals to b to the power of x, we know this is an exponential function. We know that the domain of this function is negative infinity to positive infinity, meaning those are all the numbers we can plug in, and its range is 0 to infinity. These are all the numbers we will see as the output. Then the inverse function will be called f inverse of x equals to log base b of x. So this is the inverse function. It's got a logarithm in it. And the special thing about this new function is that the domain of it is the old range, 0 to infinity, and the range of it is the old domain, negative infinity to positive infinity. Meaning what? This means that the inputs, the numbers you're allowed to plug in for x, are numbers between 0 and infinity, but not including 0. And when you plug one of those numbers in, you will see a number between negative infinity and positive infinity. That's the range of the function. So how do we interpret this new notation, log base b of x? To interpret it, you will need this definition in the middle of the page, which tells us how to convert from logarithmic notation to exponential notation. So to give you an example of what we're talking about, suppose I give you the following challenge. I ask you to find log base 4 of 16. So notice how I read this. I read log base 4, so I say the base first, and then I say the 16. So the way you should think about this is, it's a number out there. We have to find some random number. And how do you find a number? Ask yourself the following question. 4 raised to which exponent will be equal to 16? If you can find that exponent, then you're done with the problem, because that's the answer that needs to go here. So rewriting the problem will make it easier. 4 raised to what exponent will be 16? Just by guessing and checking, I think 2 is the solution, because 4 squared is 4 times 4, which will be 16. So whenever we're dealing with logarithms, we're practically trying to find exponents. So to give you another example, if I say something log base 3 of 1 over 27, you should think to yourself, what power do I give the 3 that's in the base? So what power do I give it to get at the end 1 over 27? And maybe you know this, maybe you don't, but the power that you need to write down is the power -3, because 3 to the power of -3 will be 1 over 27. So that's how we interpret this logarithmic notation. So it's really useful to know this definition on the middle of the page, because we will use it to avoid logarithms whenever possible and turn the problem into an exponential function. Turns out it's sometimes much easier to work with exponential functions. Now, saying that the function and the logarithm function are inverses just means that the graph of one of them is the symmetrical version of the other one with respect to the line y equal to x. So that's what you're seeing on the graph here in the middle of the page. It's showing us the graph of b to the power of x and also the corresponding inverse function log base b in red of x. So by the way, when I write log base b of x, the b is called the base. That's what I'm going to be referring to it as. So when I say base, I want you to think of this number right there at the bottom. It's written very small next to the log, underneath it though. And the x that you see here, I'm going to refer to it as the argument of the logarithm. So this is the argument. So when you hear me say, what's the argument? I'm talking about that value that we write next to the log. Okay, so let's look at some examples. So in example 5, it's asking us to evaluate each expression. So first, they want me to find what's the answer to 2 cubed. Then they want me to find the answer to log base 2 of 8. So the argument is 8, the base is 2. So let's begin with the first one. 2 cubed, we already know that's an 8. So that's pretty straightforward, because 2 times 2 times 2 is really 8. So that's not too bad. But what about log base 2 of 8? So what should you be thinking when you see one of these? You should be thinking, so think about this. Think 2 to what power gives me 8 at the end? And it's pretty obvious that the answer should be 3. We just did it over here. We discovered that 2 cubed is equal to 8, so we know the answer should be a 3. So that's how you solve those types of problems. It's easier to sometimes convert it from logarithm to exponential notation and then find the answer. So what about 10 to the -2? How much is that equal to? Well, 10 to the power of -2, that just means we have 1 divided by 10 squared. That's what it means to have a negative in the exponent. And 1 over 10 squared is really 1 over 100. So now the question is, what's log base 10 of 1 over 100? So again, you should be thinking to yourself, like, think this. Think, what do I put on top of the 10 as an exponent to make it 1 over 100? And I prepared you here so you know the answer should be -2. So notice that the answer sometimes is positive, sometimes it's negative. It just depends on the problem itself. There's no way to tell ahead of time whether the answer is going to be one way or the other. So that's how we do the second one. So the second one has a solution of -2. Now the last one says b to the power of 0, and it's asking me also for log base b of the argument 1, of the number 1. So log base b of 1. Well, It's also telling me just that b is bigger than 0. Why do I need to know this? Because if I have 0 to the power of 0, that becomes undefined. So it's telling me it's safe to assume that b is not a negative value or 0, which tells me that b to the power of 0 is going to be 1. Anytime I have a base raised to the power of 0 other than 0 itself, I'm going to get 1. So that's great. We already know that that is equal to 1 from formulas in algebra. Now, what about this? Well, since b to the power of 0 is equal to 1, then we will know that log base b of 1 is going to be equal to, maybe you guessed it, 0. And why is that? Because I have to think like this. I have to think, what power do I give the b to make it a 1 at the end? And the power I have to give to the b has to be the power 0, and that turns out to be the answer that we write. So this, by the way, is a formula. That last problem that we just did is actually one of the properties of logarithms, so it's kind of helpful to remember it and memorize it. Log base b of 1 is always equal to 0, no matter what the base is. So whether I have log base 10 of 1, you should say 0. If you say log base 5 of 1, the answer is 0. If I say, what's log pi of 1, you should say 0, and so on and so forth. So it doesn't matter what base I put, the answer is always going to be 0. Now, in general, in our course, we are interested in problems where the base is e, and remember e is that number 2.718 that we talked about before. So instead of writing log base e every single time of some random argument, instead of writing all this notation, it's too many letters to write, we will just do this. Instead of log base e, we will just write ln. So ln, remember that key on the calculator that we talked about a few minutes ago? ln is just a shortcut notation so that we don't have to write down log base e. So you can think of it as log base e. When you see ln, you should think to yourself, oh, the problem is dealing with the log that has base e. And some of the properties of ln are the following. ln of e is equal to 1. And again, why is this true? Let's talk about that for a second. Remember, ln is log base e. So if I say, what's ln of e, the argument, think to yourself, log base e of e. So what exponent do I put on e to make the argument show up? Well, just 1. Just leave it alone, basically. Put e to the power of 1 and you get 1. So that's the first property. The second property says log base e of 1 is equal to 0. That's what we said over here, so this is common. We already know this. The next one says log base e of e to the x is equal to x. So let's explain what this means. So log base e of e to the x, how much is that? So what exponent do I put on top of this e to make it look like that? Well, I just need to put the exponent x, because that's what I see up here anyway. So that's how you interpret that rule. And finally, the last one is the rule with e to the ln of x is equal to x. So what is this saying? It's saying that if I have e in the base and then the power is ln, but remember ln is log base e of x, well, the rule is this. E and log base e are inverse functions, so they undo each other. Just like the square root will remove a square for us, just like a plus will remove a minus for us, the e and the log base e are inverse functions. So whenever they show up together, they undo each other, and the answer is just whatever used to be written here. You just write it down as the answer. So the original argument becomes the answer because e and log e are inverse operations. So there are some other properties of logs that you may have seen in the previous course, but there's the product property, quotient property, and the power property. These are useful for helping us solve equations later on. We'll need all these rules and maybe a couple more to get through some of the problems that we will see on the next couple pages. But the product rule basically says what to do if you have log of base b of m times n. So remember, it says log base b here, but it really could be ln in reality because I can choose the base to be anything in the world, including the e, which is 2.718. So sometimes you'll see ln of m times n basically written down. Don't worry, it's the same rule as this one. It's just they're choosing a very specific base. But basically what this is saying is if you have a log of a product, then you can write it as the sum of the logs. You can write ln of m plus ln of n. So a product turns into a sum of logs. In the same way, the division turns into a subtraction, basically. And lastly, the last rule on this box tells us what to do if we have an exponent. It says you can write it down as a coefficient. So if I see something like ln x squared, for example, in a problem, this rule allows me to write 2 ln of x. So it allows me to remove an exponent and place it in front of the logarithm. So this is a very, very useful rule, and it's one of a kind. It's very useful whenever the exponent is bothering you and you want to remove the exponent. You just put logs into the problem and the exponent disappears, basically. In the same way, sometimes we have problems where you have like 4 ln of x, and the 4 is inconvenient. We don't want the 4 there. So we can use the same rule to write the 4 on top of the x. So we can swap it and write ln of x to the power of 4. So it's just, we can be used both ways, basically. Now, this last one is useful for some of the older TI calculators that don't have dedicated ones with log any base. Sometimes we'll have to plug in some logs into the calculator, and this formula in this page allows me to rewrite my problem any which way I want with different bases. So the useful part is this right here, which says log base a of x is equal to log base b of x divided by log base b of a. So what does that mean? Suppose I'm doing a problem where my calculation says we want log base 13 of 71, for example. For whatever reason, this is the answer to the problem, and you want to be able to plug it on the calculator. A lot of calculators don't come with the base 13 or a key for it even. So what do you do in that case? You just convert this to a brand new base using the change of base formula. So you can rewrite the problem as a fraction, and the most calculators, almost every single one of them in the world, will have a key for ln somewhere. So you can write ln of 71 divided by ln of 13 instead of the log base 13 of 71. And so this can be done pretty much with any calculator, whereas the original one, very few calculators have a dedicated key for log base 13. It's not very common, so that's why it doesn't have, that most calculators don't have it. So with this in mind, I know this was a crash course, but most of you have seen some kind of logarithm before, so that's why I'm going through it quickly. And really, we want to focus on the calculus later on, how to find derivatives and so on of these things, maybe antiderivatives later on in this course. But for now, we're just going to go through a couple of applications and how to solve certain types of logarithmic equations. So let's look at example number 6, where we see our first application of logarithms in real life. So this is the Richter scale. Maybe you've heard of it. Whenever an earthquake happens, somebody will say, oh, it was magnitude 7 or magnitude 3 or magnitude 5. What are they talking about? And so let's look at example number 6. So the Richter scale is a scale used to measure the magnitude of an earthquake. The scale is a base 10 logarithmic scale. So what does that mean? That means that the formula that we use has a base 10. The most common bases in the world are base 2. If you're dealing with computers, it's going to appear everywhere. Log base 10, if you're working with, in this case, earthquakes or sound, that's a very common base that appears in those types of problems. And finally, ln, which has basically the base e. That's a very common one in calculus, or if you're studying the population growth. So if you're dealing with some kind of application that has to do with biology, log base e will appear very frequently. Now we're told, given two earthquakes with magnitude R1 for the first earthquake and R2 for the second earthquake, on the Richter scale where R1 is bigger than R2, suppose the amplitude of the first earthquake, suppose the amplitude of the earthquake's waves for these two earthquakes are A1 and A2 respectively. Okay, the amplitudes and magnitudes of these earthquakes must satisfy the following equation: R1 minus R2 equals log base 10 of A1 over A2. So let's talk about this. We have two earthquakes with magnitude R1 and R2, and apparently R1 is bigger than R2. Okay, great. Now, the amplitude is also given to us for these two earthquakes. The first earthquake has amplitude A1, and the second one has amplitude A2. And we're told that there's a relationship between the amplitude and the magnitude, and it's described with this formula over here. Okay, so far, all of this is basically nonsense. What do they want me to do? They're saying, suppose one earthquake measures 8 on the Richter scale, and the second one measures 6 on the Richter scale. How much more intense is the first one compared to the second one? So, in other terms, here's what's going on. We're told that one earthquake measures 8 on the Richter scale, so that means the magnitude of the first earthquake is 8. And we're told that the second one is going to measure 6 on the Richter scale. How much more intense is the first one compared to the second one? So figure out what A1 is and what A2 is in terms of each other. So is A1 10 times A2? Is it 100 times A2? Is it 1,000 times? How much worse is the first earthquake that has magnitude 8 compared to the second one? Well, using the formula, we know that R1 minus R2 is equal to log base 10 of the amplitude A1 divided by A2. Okay, we know that R1 is equal to 8, so let me get rid of everything else. So we know that this guy here is 8 minus, we know that R2 is equal to 6. That's what we're told. So we know R2 is equal to 6. And we're supposed to figure out what A1 is in terms of A2. So we can compare which one of these earthquakes is more intense, or in reality, how much more intense is the first one compared to the second one. Okay, so by the way, 8 minus 6 is really 2, and so 2 is log base 10 of A1 divided by A2. And we are going to be stuck with this logarithm base 10, but we really prefer not to have logarithm notation. So this is where I'm going to use the definition. So remember, the definition says this. It says if you have y equals to log base b of x, you can rewrite this problem as b to the power of y equals to x, meaning just take the base, push it under the y, and then drop the logarithm, and you get this equation. So for me, I'm going to take the base 10, push it under the 2, and then drop the logarithm from the problem. That's how I can rewrite it without the word log in there. So that's how I can convert from logarithm notation to exponential notation. So take the 10, put it under the 2. So 10 is the new base, 2 is the power now. No more log, and we just have A1 divided by A2 left over on the right-hand side. But 10 squared is really 100, and that's A1 divided by A2. So what I'm saying is that A1 is equal to 100 times A2. How do I get this last answer? How do I get that A1 is 100 times A2? Well, I'm thinking of it like this. 100 divided by 1 is a fraction. It's equal to the ratio of A1 over A2. So it's one fraction equal to another fraction, so I can just cross multiply the fractions. So 1 times A1 will be the A1, and 100 times A2 will be the 100 A2 that we see at the end. So what are we saying? We're saying that the earthquake measuring 8 on the Richter scale is 100 times more intense than one measuring 6 on the Richter scale. And this is what I'm writing over here, that the implication is that an earthquake measuring 8 on the Richter scale is 100 times more intense than an earthquake measuring 6 on the Richter scale. So that's an application where we see logarithm, and now what I want to do is talk about different ways to solve equations that contain logarithms and exponentials. So we're just going to go quickly through all these because some of them are probably review for you, some of them may be new. So if you are having a hard time, please see me in office hours or talk to me, send me an email, and we'll talk about how to fix your problems. So 2e to the power of x is equal to 7. This is the first equation. It's got 2, the base e, the power x. So this is all an example of an exponential function because the power is the variable, x is in the power, And we're basically going to have to find two answers, one exact form and one rounded to 3 decimal places as appropriate. Okay, so how do I solve an equation like this? So the idea is isolate the base that has the power. So isolate the e to the power of x. And to isolate it, I must just get rid of the 2. And so keep in mind that 2 right now is being multiplied by e to the x. So to remove the 2, we do the opposite. So we just divide both sides by 2, and this gives us the e to the power of x is equal to 7 over 2. So we're not quite done yet because we need x to be in the base, not in the power. So to get it into the base, not in the exponent, we will just introduce ln of the whole thing. So we will do ln of e to the x because we have a property that moves the power to the front if there's an ln. So I'd like to get rid of the x and remove it from the power, put it in front. So I'll just introduce logarithms into the problem. And whatever you do on one side, you got to do the same on the other side. So now, according to one of the rules we saw previously, this x that was in the exponent gets to be removed and placed in front. Now that there's an ln, we are able to do that. So x ln of e is equal to ln of 7 over 2. But really, in reality, ln of e is really just 1. And why is that? Remember, ln of e, that's the same thing as saying log base e of e. Remember, ln is notation for log e. So this ln replaces log base e. But what exponent do I put on top of this e to see the argument at the end? Well, the exponent that I need to put in is just 1. So this is why we can say that x times 1 is equal to ln of 7 over 2. But x times 1 is just really x. And so the exact answer is that x is ln of 7 divided by 2. If you like, you can use other properties of logarithms to write it as ln of 7 minus ln of 2 if you like, because a fraction, ln of a fraction, is the difference of ln's. But anyway, let's see if this is true or not. So this is the exact answer. Choose one of them. I prefer the first one, obviously, because that's more compact. But the other second one that we wrote is also correct. It's not wrong. But let's see that this is true by using our calculator. So let's type in ln of 7 over 2. So ln is the key right next to 4. So this time I don't need to click any second keys first. I just type in ln and then 7 divided by 2. Don't forget to close the parentheses. So you see it says 1.2527. Or if I had typed in ln of 7 minus ln of 2 with appropriate closing parentheses at every point, then you see the answer is the same. So that's what we were talking about earlier when we said one of the rules allows me to convert from ln of a ratio to the difference of ln's. So the bottom line is, roughly speaking, the answer is 1.253 because we're running to 3 decimal places. That's what they asked us to do. So I'm going to write that next. I'm going to say, or roughly speaking, x is roughly 1.253. In math, we prefer exact answers, so this is the best answer we can write, but this is also appropriate, or this is also appropriate, so it's up to you. So that's the end of the first one. So the second problem has 4 times 5x plus 3 in the exponent. So this is the exponential part, minus 8 equal to 28. So this is an exponential function again, because the x that we want is in the power, so great. How do you solve it? Well, isolate that term. Get rid of everything else, keep this term all by itself on one side of the equation. Once you've done that, put ln on the left, put ln on the right, and keep going. So what that means for me is this. First, the 8 must go. So to remove it, I will add 8 to both sides of the equation. So adding 8 to both sides of the equation gives me 4 times 5 to the power of x plus 3 equal to 28 plus 8 will be 36. Next, I need to get rid of the 4. Right now, the 4 is being multiplied. So what do? I just divide by 4 on both sides of this equation. So this means that 5 to the power of x plus 3 is going to be 36 divided by 4, which is 9. Remember, 4 divided by 4 is 1, and we don't have to write down all these extra ones. That's the whole point of doing this. So now, focus on the variable. The variable that we want is in the power. So I need to get it out of the power. So what do? I write ln on the left side of the equation. So on the right and on the left, put it ln, but it's always going to be placed on the left side of all the notation. Right, so ln of 9. So please don't write 9 ln like this. It doesn't have any meaning when it's ln by itself, right? The ln has to have an argument, so ln of 9 afterwards. So squeeze it between the equal and the 9. So the tricky part is that the whole power needs to now be moved to the front of ln. That's what ln allows me to do. So I'm going to write x plus 3 with parentheses and then ln of 5. Okay, so that whole power needs to be in front and they all need to be multiplied with the ln 5. That's all equal to ln of 9 on the other side. Now, ultimately, I'd like the x to be alone. So to get x alone, first I need to get rid of the ln 5. Then I need to get rid of the 3. So ln of 5 right now is being multiplied, so we will divide both sides by ln 5. And whatever you do on one side, you got to do on the other side. So x plus 3 is equal to ln of 9, all divided by ln of 5. And finally, the 3 must go. So the 3 is being added. So to make it disappear and show up on the other side, I need to subtract 3. So the final answer is ln of 9 divided by ln of 5 minus 3. So this is the exact value. But if you like, you can write it in a different way. Using the change of base formula, instead of having ln of 9 divided by ln of 5, you can write this instead. You can say, instead of ln, log base 5 of 9. That's another appropriate way to say it. And then minus the 3 on the side. So again, both of these are acceptable, but my preferred one is the first one. That's the same that we got from the problem. It doesn't have any extra stuff going on. There's less chance for error there, so that's why I prefer this notation. So now that we have the answer, we want to figure out what it is as a decimal so we can find out and give the answer back to the problem. So let's make it a little bit smaller to fit it first, and let's put it into the calculator. So I'm supposed to type in ln of 9 divided by ln of 5 minus 3. So going back to my calculator, type in ln of 9, make sure you close the parentheses, divided by ln of 5, make sure you close parentheses, and then everything has to get subtracted by 3. So the solution is negative 1.6347. We're rounding to 3 decimal places, so we're going to say 635. So negative 1. Roughly speaking, negative 1.635. That is my x value for this problem. Now, some of you have a fancy TI calculator that can do logarithms with other bases. So if you have one of the newer TI calculators, I would like you to click on Math next. And when you click on Math, there's an option from the bottom of the screen. It's easier to find it from the bottom of the screen. Under Math, the first column has log with the word base next to it. This allows you to put into the calculator log with any base. So this is only available on some of the newer TI calculators, not available on the older ones. So don't be afraid, or don't worry if you're not finding it. It's probably not just found on your calculator. So for me, I would type in log base 5 of 9 like this. I would type in log base 5 of 9 as 9 comma 5. So I would type in the argument first, then the base, then I close with minus 3. And if I do that, you see I get the same solution. So I'm just showing you that it's okay to convert from ln notation to logarithm base 5 notation. It's not a problem. This is all going to be the same. Sometimes it's useful to have this answer. Sometimes it's useful to have this answer. But the bottom line is they're both the same as a decimal. They're both negative 1.635, roughly speaking. So now let's turn our attention to basically logarithmic problems. So what if I have a logarithm in my problem and I would like to solve for x? So I would like to know what x to plug in there, so that log base 3 of x plus 7 minus log base 3 of 2 equals 4. Well, for these types of problems, we have to use the product, quotient, and power rule for logs. So the idea for these problems is to combine the logs on the left side into one single logarithm. And to do that, I need to pay attention to the number or the plus or minus in the middle. So first, let me start by writing down the problem, log base 3 of x plus 7 minus log base 3 of 2. This is all equal to 4. First of all, I want to make sure that there's a 1 in front of each log. If it's not a 1, then I will take the number and put it in the exponent. That's the first step. Now, in my case, they're both 1s. So the next thing I do is pay attention to the minus sign. The minus means I can rewrite this problem instead of a difference as one single log of a ratio. And the numerator will be x plus 7, the denominator will be 2. So the minus allows me to convert the problem from a difference of logs to a log of a fraction. That's allowed because of the minus sign there. Now, the numerator will be x plus 7 because that's the first argument, and the denominator will be 2 because that was the second argument. Now, there's a log base 3 of some kind of fraction equals to 4. But I don't like the fact that this problem still has a log, so I'm going to rewrite it without the word log. And how do I do that? I do that using the definition. So remember, the definition is this: y is equal to log base b of x. This means what? It means that b raised to the power of y is equal to x, meaning I can take the base, shove it under the y, and then drop the log from my problem, and that will be okay, as long as I put an equal in the middle. So I take my base, shove it under the other side, and drop the word log, and that will be okay. So in other terms, I can write down x plus 7 all divided by 2 equals 3 to the power of 4. This is perfectly acceptable to do. Okay, and so now 3 to the power 4, this is basically 3 times 3 times 3 times 3, 4 times. This is really 81, so I can do that first, rewrite it as 81. And remember, 81 has the invisible 1 underneath it, so we can now cross multiply the fractions because we have one ratio equal to another. So this means x plus 7 is going to be the same thing as 2 times 81. And if you already know what 2 times 81 is, you could just write down 162. And finally, x is going to be 162 minus 7. And again, if you know the answer directly, just write down 155, and that will be it. Now, there will be times when you have multiple answers, and it's always a good idea to plug in the values there to check that the answer actually works. For this one, I'm not going to do that, but for later on problems, it's useful to plug the number in and make sure that the number that you're getting as your final answer actually does work for the problem. There are times when we have something called an extraneous solution where the answer that you get is a fake answer. So like, for example, if I got something like x equals to negative 10, I would instantly know that there's a problem because the domain for these logs should not be negative values. I shouldn't have a negative number inside of my log. So then I would know that something is wrong, and I would just say, oh, that's an extraneous solution. So cancel it out. It doesn't count. Okay, here we go again one more time with 2 ln of x plus ln of 4, and it's all supposed to equal 1. So again, the idea is to combine all the logs into one single log, and in order to do that, we need to have a 1 as a coefficient, but right now I have a 2 on one of them. So what does that mean? That means we're going to start by moving the 2 to the exponent of the x. We're going to write ln of x squared plus ln of 4 equals to 1. So that's the first step. Next, I'm going to notice that there's a plus sign in front of the ln 4, which means I can convert this ln plus ln into ln of a product of things. And the product will be the product of x squared and 4. So the sum of natural logs, or the sum of logs, can be turned into a log of a product. And the x squared is the first argument, so it goes first. And 4 is the second argument, so it goes next. It's all still equal to 1, so we just keep writing down the 1. Now this means x squared times 4 inside of an ln is equal to 1, and I'm trying to figure out what x is. So what do? First, let me rewrite it without all the colors, and let me write 4x squared instead. And to get rid of ln, what I need to do now is put it as a power of e. because e and ln are going to cancel out. And whatever you do on one side, you do the same thing on the other side. So in previous problems, we put ln on the left and right. Now we're putting e, but we're putting it as a base underneath all the numbers. So we're basically saying that e to the power of ln 4x squared is equal to e to the power of 1. And that's because e and ln are inverse operations. They undo each other, meaning 4x squared will be equal to e to the power of 1, which is just simply e. Remember, e is roughly 2.718, so just approximately in your head, think like 2.7 is there. So do the same thing that you would normally do if you have a number. Well, if I had a number and I'm looking for x squared, I would just divide both sides by 4. So it's going to be e divided by 4. And if I want x itself, I would have to basically square root both sides. But keep in mind that you need a plus or minus whenever you square root a quantity like this. Now, is it possible to have both plus and minus as the final answer? That's the question. So let's go back to the original problem. The original problem had ln of x, and ln is a logarithm function, which means it cannot accept a negative solution. It should only have a positive argument. So the final answer is not both plus and minus square root of e over 4. It's actually just the positive version of e over 4. So the negative 1 cannot be counted in as a solution because it would mess up the natural log. So this is the answer. Now let's put it on the calculator and see how much it is equal to. So the square root of e over 4. So I want e to go next. So I can go e to the power of 1 and divide it by 4 and then close the parentheses. So the answer is 0.82436, but we're running to 3 decimal places. So we'll just say 824, so 0.824. For the previous one, I had 155, so that's why I did not need to put it in the calculator. I mean, it was pretty obvious, and we couldn't round it. But for this one, we already have 0.824, so I'll just put another box around it, and I will take off the box from the other one because it contains one of the extraneous answers. Okay, so the last thing we're going to deal with here is the same kind of oil-rich country problem that we dealt with in an earlier part of this video. We're told that there's a function that estimates the demand for an oil based on the P, which is the price of barrels of the price P in dollars of a barrel of oil. And the question is to find the price point needed to create a demand of 12 million barrels. So we want to know the P if the answer here is 12. So what number P do I plug in to get 12 as my demand? So the demand for P is 12. So in other terms, solve the equation 12 equals 150 times 2.7 to the power of negative 0.25 P. So that's what we're being told to find. Well, let's focus on the variable. The variable is there. So we are going to try to solve the equation by trying to isolate the term that contains the variable. So that means this term must be isolated. So that means the 150 needs to go away. Right now the 150 is being multiplied, so I'll just divide both sides by 150. So 12 over 150 will be the 2.7 raised to the power of negative 0.25 P. So now, again, focus on where P is. P is in the exponent. I'd like it to be outside the exponent. I'd like it to be away from the exponent. So what am I going to do? I'm going to introduce natural log on both sides. The reason why is because natural log has that cool property that takes an exponent and writes it in front as a coefficient. And that's good for me because then P will exit from the power, it will become a coefficient, and then I'll figure out what to do with it later on. So that's what I'm going to do next. I'm going to type in ln of 12 over 150, and we can put this in the calculator in a few minutes. It's going to be negative 0.25 P times ln of 2.7. And ultimately, we would like to know what P is. And currently, P is being multiplied by negative 25 and by ln of 2.7. So to get what P is, we'll just divide by both of those quantities, and that will give us the P that we're looking for. So P is ln of 12 over 150, all divided by negative 0.25 ln of 2.7. So that's what P is, and you know what? Let me write it in front of this so that it's easier to see it. And we will just need to plug it into the calculator to get the value that we're searching for. Okay, so be careful typing all of this in. So first we need to type in the ln of 12 divided by 150. Make sure you close the parentheses for the end of the ln, and this is the end of the numerator. So next I'm going to put my division sign, and my denominator contains a lot of terms with the negative 0.25 and everything else. So I'm going to want to use parentheses here with the negative 0.25 going first, and then I'll multiply that with the ln of 2.7. Now, ln automatically opens up a parentheses, so I'm going to have to close 1, and I put 1 for the denominator, so I need to close the denominator parentheses as well. And when I click enter, the answer is going to be 10.1715, and this is money, right? So, or millions of barrels or whatever. The P that we're looking for is actually dollar amount, so it's appropriate to round to 2 decimal places, because remember, P is the price for the demand to be 12 million barrels. So the P that we're searching for is, roughly speaking, 10.17. So at $10.17, we will have 12 million barrels of oil demanded.